Okay, so the next problem in the lead code we are solving is implementing the tray. Okay, this is also called as a prefix tree. Let's see like how this works first. Okay, and then we can see like, I mean, we'll be solving both of the problems. One is this and also this one. Okay, like almost similar, like will be some difference will be there. So let's quickly try to understand what is this tray data structure, and then we can quickly see like how to insert the nodes and why it is useful for, and all those things. Okay, so basically this try data structure is useful to search for a words. Okay, like, or we can say an auto suggestion. Let's say that when you are typing in a mobile, right, like, I mean, you will be getting some suggestions, right? So that's where this application of this data structure comes in. Okay, so basically what will happen is we'll be having a root node. Okay, we'll be having a root node. So let's say that I want to place a word called and. How are we going to do it is, okay, before that, one basic thing we need to know about this here is, and if you take a tree data structure, like what will be the structure? There will be a root node, and there will be right node attached to it, and there will be left node attached to it. Okay, like, I mean, there will be some one-way connection to it, right? There will be a connection. But here, what is this tree data structure will do is, it will only consist of the alphabetic characters. Okay, and oh, sorry. So it will have only alphabetic characters. So it will have the mapping. So it can have at most 26 mappings. Okay. So here in the tree we had only one to two linkings, right? It's a binary tree. So like in the graph, like it can vary, correct? So similarly in the tree data structure, what will happen is where he'll be having some node, and it can have mapping to the 26 alphabetic characters. It's like at most. It's not like every time we should be having 26. It can be one, two, or three, anything like that. Okay, so now let's say that we'll be having a primary node, root node. Okay, now we need to build a try data structure such that it will helpful as in generating a suggestion for the users. Okay, as soon as they type, we should be able to add it. Okay, now let's take this example and add and do. Okay, now how are we going to add it is, so as we said, this will be the root node, right? So this can have like at most 22 child runs. Okay, so we'll take the first character a. Like, how are we going to insert is, so we'll check if there is a node is present or not. A node, it is not present. So what we'll do is we'll add a node here. Okay, we'll add a node here, and then what we are going to do here is, next is we want to add an n. Okay, so we need to build a suggestion, right? Basically, like, I mean, after a going a, we need to add n. So does a have any nodes? Still no, right? So what we'll do is we'll add a n here. We'll add here n. Okay, and finally when there is a d, okay, a n, and we came here and there is nothing for nothing, d character is not there, so we'll say this is the d. Okay, and when we come here, we'll say that declare this as a end node, like some flag for this one or something. This is a node ultimately, right? This is like a class and object. We'll set a property called end node so that we know that we are traversing the till the end. Okay, this is one thing. So now it will be clear like how this data structure is coming to picture here. So now a and t. Okay, similarly what we'll do is we'll need to add a here. So a is already there, we don't need to add a new node. Okay, there should not be any duplicates. So a comes here, and then we need to add a n. So do we need to add n one more node? No, there is already one, we can reuse it. Okay, n is there. But when it comes to t, so d is already there but t is not there, right? So we'll have to add it. Okay, so now we can check an example. Okay, so now when the user starts chatting, and okay, and now he types a n. Okay, so based on this, if he, as soon as he type a, we can suggest him that whether he is typing a and d or a and t, right? Like, I mean, if you traverse, like, the possibility is two paths. So he's taken this path. Okay, like let's say that there is a one more word called b here. Okay, there is some word starting with the b. We don't care about it. They started typing a, so we will be showing only a and d and a and t. Okay, this is one thing. Let's say that he types an, so still it will be valid. Okay, and now at the finally, like when he say, let's say that there is one more word here called b. Okay, a b c, something like that it was there. Okay, so as soon as he type a and n, we will be showing only dt, a and so we don't show abc. Okay, if you understand it, I think it will be clear, right? So I don't think there is nothing much to understand here actually. So this is the root node. We will be height, we can have at most 26 childs. Okay, and it can have at most 26 styles, and it can have only alphabetic characters. So we will be placing the characters such a way that it will be helpful for our generating a suggestions. Okay, now let's see that how we are going to build this tray data structure. Okay, so as we discussed so far, right? Let's see like how we are going to implement this. So basically, first we'll have to insert it. Okay, this problem is about implementing, inserting, and searching, and also checking if the word is starting with the some word or not. Okay, so first we need to build a insert function, right? Like, I mean, how are we going to build it? So initially we'll contact create it a root node. Yeah, and also this will be useful actually. Like we initially, like each of the node, in the consist of the binary tree, what will be there? Left and right, right? Self dot left, self dot right, right? Left will point to one node and right will point to node one other node, correct? So here similarly what we need to do here is we need to make use of an heap data structure to check, like, I mean, 26 nodes, right? Like, I mean, we cannot have like 26 object here, right? Does not make sense. So we'll be having all the childrens in one under this one, and we'll have a mapping like this: a is mapped to this node, b is mapped to this node, c is mapped to this node. So what will happen, so whenever we are trying to generate a suggestion, right, we'll check if the a character exists in this heap or not. If it is present there, we'll be considering that for like next pass building. If it is not, we'll be stopping there, we'll not consider it. Okay, so this is how the try node looks. Mm, it will be having a heap, or we can simply say dictionary. Okay, a dictionary that is mapping the character and its node. Okay, so now what's going to happen here is, let's say like we want to build this tray node. Okay, so we have been given the word called apple. Okay, so what we'll do is we'll iterate through the word. Okay, and whenever we are doing iterating, we will see like if that character, whatever the character that we are going to try, if it is already there or not. If it is already there, we'll move that pointer to that node. If it is not there, we'll create a node. Actually, we'll be in the children's list, right? We'll update that heap, or we can say that dictionary. We will update that mapping, and we'll move our pointer to the next one so that we can insert to the new node. Okay, so what has happened here is, so we'll start from here, root node. Okay, and we'll start checking the each of the characters for character, each of the character, and we'll see if character is present in the current children node. So it is like what we are currently doing is, this is the root node, and we are seeing if that apple, like, these nodes are not present. We are checking if a is present under this child of this root or not. If it is not present, we'll have to add it. Okay, this is that. If char is not in this one, add a new node and add a mapping for this. Basically this children's, add a mapping for this, and this will be the node. Okay, and yeah, like if it was already there, right, we could have directly we could have directly gone there, but it is not there, so we'll have to do it. Okay, so now current curve will be pointing to this one. Basically if you are trying to add an and word, right, like currently it will start pointing to this one. Okay, so now what will happen next is, similarly when the next word is apple, right, next word is apple, so we'll come here. Yeah, we it is pointing to a. We'll see like if there is a character p under it. So if it is not, we'll be creating now, creating new, and it will be moving our pointer. This is how the insert works. And once we are done with the insert, right, we'll have to search through it. Okay, let's say that I will ask for a word apple, search for an apple. Okay, we inserted this apple, and we'll have to now search for an apple. So similarly we'll point our start from the searching from here. If anywhere it is not present in the child, right, so we can declare it as false, it is not found. If it is found, we'll have to move our pointer to the next one. So basically as we discussed before, right, we'll check here first. Let's say that we'll check here first. We want to look for a, so we'll look here. Okay, and then if you want to look for some other character, let's say here it is n, it is found. But let's say that if I want to look for a b c d, okay, but b is not found, so in that case we can simply return false, saying that this search is not found, this word is not found. Okay, ultimately let's say that how, like when we are going to say it is found, meaning like if we once it is fully found. Okay, so let's say that we are looking for a word dad. Okay, so d is here and a is here, and when I search for d, this is also here. We had marked this, right, we have marked this as an end node, then we are good here. Okay, so let's say that instead of dad, so it was like daddy or something. Okay, e something like that. Okay, GIDIE. Okay, so let's say that if I'm looking for a dad word, dad is not found, daddy is found, right? We'll have to also have to look for an end node here. So let's say that in this tree, if you're looking for a dad, it is not found. Like we are not talking about a starts with, it's like a full search it should be, right? If we are just looking for a dad, it won't be now, it will, like, I mean, the answer should be false here. Okay, so that is it actually. Like that's how the search should work ultimately. Like, I mean, we'll keep on searching it, and let's say that whatever the node we are currently pointing at, it should be at the end. If it is not, we should be returning it as false. So that's why like, I mean, if it is like that, will be there, just like search is not found. And also one more thing to tell here is insert, right? Once we are done with it, once we are done inserting it, we should mark ourselves that node as an end node, so that here it will be helpful to decide like if it is we are at the end, or if it is like still the sub part, right? Yeah, as we just check, right? Okay, I think that's a spelling wrong, right? Daddy. So DDY, right? So yeah, my bad. So let's say that y, right? So yeah, so like I mean we are not looking for a start with or substring, full should be a full match, right? So that's why this flag is helpful, dot end. Okay, so I think now it is clear actually. So insert is done, search is done. Now if you want to check for a starts with, right, we don't want that flag basically. What we'll do is we'll do this exactly the same thing. Okay, like there is a duplicate of code, but yeah, like that's okay for this one. So for character, okay, and let's say that if character is not in this, right, we'll return a false. If you are able to iterate through all of the given prefix, okay, and we can simply return as true. But when it comes to search, it should be a full match. So that's why we'll look at this flag, whatever the node currently we are at, if it should be true, else we'll be returning it as false. Okay, this is how the insertion searching starts with works. Okay, so now if you check the, like what has been asked here is in the next problem, what has been asked here is we had to design the add and search. Similarly, like I mean we already added it, right? It's the same thing, but here they're asking for a search. Like search also we did it, right? What is the difference here is, so currently it is like we have added apple, they asked for an apple app, like this kind of was the structure. Okay, but here what they are going to do here is kind of implementing the regex also, regex expression. Okay, one is simple expression it is. So they have given us a dot actually. So let's say that if they've added the word this thing, okay, they've added a bad, dad, mad, okay, and bad, okay, and again this bad. Okay, so if they are looking, okay, sorry, it is a searching, they are searching for bad word, okay, word bad. So it will be matching, right? If you draw the tree, like it will be clear actually, bad, it is match, right? But we should also be matching for this also, star dot ad. So whichever the matches, right, like if it is matching, we just have to send true or false. Okay, this is the problem. This is the same problem of tray. So as they've asked for a searching the words, right, searching the word data structure, we can simply go for a tray data structure, like, or a something like prefix or anything, right? We should be going for a tray data structure. Okay, so now how to do this, right? Like I mean we have done this already, like to search from start to beginning, and also we have done for a start with also, but how to do it for a dot. So basically what we need to do here is, first we can solve this either by a DFS approach or BFS approach. Okay, so basically what does it mean is, let me clear this. Okay, so right, this for searching this one, right? I can say here it is an and, right? So let's say that I can search like dot and, or I can give dot and dot. Okay, like okay, it should be like this. Okay, so that it will be easy to why how that works. Okay, if I'm looking for this one, okay, I can give it like this. So now what we need to do here is, if I say dot should match all of the character in the regex. If you know how the regex expression works, dot should match all of this character irrespective of it, we should be considering it as a matching. Okay, so now what we are going to do here is, like if we are using the breadth first search, meaning like we should explore all these nodes first before actually going to there before, right? What should be doing is, we should be getting all these nodes, like as we have a mapping, right, children's, and again that's a dictionary here. Okay, right, we can get all the values. So once we get all the nodes, what we'll have to do here is, like we'll have to kind of use each of them. Okay, so it's like once we'll consider all of this node at once. Okay, and then what we'll do is, we'll pick this one. Okay, we'll pick the node A, and then we'll check the child node if the next character is matching or not, if the whatever the character that we have, right? If it is matching, we'll consider it, will, or else we'll be ignoring it. This is how the BFS works. So let's quickly check that. That will be straightforward to understand. Then we can see like how the BFS works here. Okay, so what we'll do is, let's say, okay, let me explain the other way around also. This is the character match. Okay, like I mean A is, if A is, let's say that if I'm looking for A and D, what I will do, I will directly match the character A, I will character match N and D, right? This is good, this is straightforward. But let's say that if it was a dot, let's say if it was a dot, like I mean dot an dot and I should be considering all of this. Okay, that is one thing. This is a two rule that we need to keep in mind while solving this. So what we're going to do here is, we'll be initially setting to our root node. Okay, and here, right, if you're solved, we can also make use of a queue, like right, like I mean usually BFS, that's how we are going to do, but I've just written a different way here. Okay, so what we're going to do here is, it's a list. Okay, like I mean because we need to deal with the multiple number of nodes, so that's why we have declared it as a list instead of not single node, it has been list here. Okay, so for each of the character, we'll check if it is a dot or not. Okay, if it is a dot, we'll be having a different approach. If it is not a dot, we'll be having a different approach. Okay, so let's see how we're going to do. So once if it is a dot, right, we'll have to consider all of the nodes, right? I mean all of the nodes as a valid. Okay, so we'll see, we'll update our nodes. Currently we have only one node to handle, so it's only with one. But let's say that here, right, we have considered a dot en, right? All these are valid, so we need to consider that base as like list of nodes. Okay, so this will be the for node of nodes. Okay, so we have considered all of these things now. So every time we do the analysis, whatever the nodes that are eligible, right, whatever the nodes that are eligible, we'll have to do our analysis. So let's say that, okay, we have filled our all the eligible nodes. Okay, so this comes under eligible now. Root is fine, as this is dot is matched with all of this, we have considered this as eligible. So next time when I'm looking for n, I need to look for in a node also, like I mean the first node also, I need to look for in the d node also. If it is not present in any of the node, we'll be skipping it. Here you can see d is not present, n will not be present in this, right, we'll be eliminating this one. Okay, so basically we'll be iterating through all of these nodes. That's what we are currently doing here. Okay, so let's say that if we got any character, so we'll be checking for each of the nodes that if it is present in the node dot childs or not. It means if it is a, like I mean whatever the character we found, if it is present under this or not. If it is not present, we don't need to consider it. Okay, we'll ignore it. Okay, whatever that is present, we'll be picking it. Like it's a short code for using in the list comprehension. Okay, so if it is a dot, we will be getting only the values. I mean all the nodes will be considering it as an eligible, and we'll be trying to match with the upcoming character also. Okay, and also let's say that if there can be chances like two dots, okay, like here also, right, we should be considering all of the nodes again. Like I mean we'll be dropping those all of these nodes, whatever the nodes that, yeah, we should make sure that we should, whatever the levels, right, current level is this one, we'll be dropping all of this, and we'll be picking the new number of sets, because we don't need this, right, once we consider that all of these nodes, we don't need the previous ones, correct? So yeah, that is it actually. So anything else? Yeah, this is how the search by BFS works. So first explore full level at once and then go for the next one. So DFS, yeah, like I mean it's like using a recursion. Let's see how does that go. Okay, this will be like kind of straightforward thing, but yeah, like I mean whichever suits for you guys, like I mean you can use, but this will be like more efficient DFS. Okay, like this will, as we are storing everything in the list, like this will increase the space complexity and everything. So yeah, now let's check the DFS. So what we're going to do here is, so we'll be picking one node here. Okay, one node here and perform the DFS. Once that is done, we'll going for a next node. That is the difference between the BFS and DFS, right? So what we're going to do is we'll be passing the word to it, like what is the word that you are going to search, what is the starting index, and what is the current node. Okay, so initially we will send the full word and the index as 0 because we are starting for just now, and the node is root node because we are going to start from a root. Okay, so this will be the exit condition for us, like when the index has reached the final, right? And also like if it is an end term, like we are going to search it, not a start word, right? So we'll be looking for a parameter, like I mean this attribute, if everything is in the end or not. If it is end, we'll just return the true. Okay, so finally the same thing as we discussed before, like what we are going to check is this will be our base condition, and we'll check if the character is equal to dot or not. If it is a character is equal to dot, it will be having one behavior. If it is not equal to dot, it will be have one other behavior. That's what we are going to discuss here. Let's say that if it is a dot, right, so we'll have to analyze rest of the function. Like I mean we'll just pass that node to the we'll just pass that node, like whatever that node, right, that will be there, will be performing the DFS, all the eligible nodes, like we'll be picking all the eligible nodes here, and then we'll be performing the DFS individually. Okay, like basically here we have considered that node itself as a valid one, dot is a valid one, so we have performed the DFS here for all of them. Okay, let's say that if some character is there and the character is not matching, character it doesn't match with any of the child nodes, we'll just simply return as a false. If it matches, we can just pick that node and analyze it for, send for a further analysis. Yeah, I think it's a bit like I mean kind of lengthy video, like, and I'm just trying to explain in the, like I mean very top level, but once you implement this, right, it will be more clear actually. That's all I can say. Search for a BFS and search for a DFS. Like I think one thing that we need to keep in mind strongly here is when it comes to searching for a data structure, like I mean auto suggestion, maybe building such data structure, right, we can make use of a tray data structure here. Okay. Okay, sorry, got distracted. So, okay, so to summarize here, like I mean, this tree data structure needs to be used when we are implementing like auto completion features, right? The tree data structure will be useful, and most importantly, like few things that needs to be remembered here is, like I mean, on top of that, if we knew this information, we can keep on building the data structure here. So basically, like try order data structure will look like this. Okay, this all it will consist of at most 26 styles, and it can consist of only alphabetic characters. Okay, and I think it can also have the special character also, but yeah, I don't see any drawback in using the special character. But at least there should not be any duplicate, I believe. Yeah, there should not be duplicate at any cost. So because like I mean we cannot actually navigate properly, right? Yeah. So yeah, this is the tray node, and it can be used for auto completion, and it can have at most 26 childs. And at the end, we'll mark it as a mark it as an end node, so that we'll know that we have reached the end node, and it will be easy for traversal. Yeah, that is it. We can. And also for this specific implementation, like I mean to implement to fix the dot character, like I mean to make the search work for dot character, we have used the two approach here, either CBFS or DFS. Both works in this way. Okay, this is a DFS approach and this is a BFS approach. Yeah, that's it. Thanks.